All right, so next one is Dr. Venkatesh Ramaswamy, the RIC to rescue. I think there's a question about RIC. How intelligent steering could help ease telecom spectrum shortage. And he's the chief technologist at MITRE for NextG. And Venki also has been a frequent speaker at IEEE event. So Venki, all yours. You have about 20 minutes. And Venki was supposed to be on site due to personal reasons, so he had to stay back. Thanks, Venki, for your time. Can you speak?
Can you see my slides?
Yeah, we can see your slide. We can hear you also. Please go ahead.
Okay, great. So first of all, thank you so much to Ashutosh for inviting me. This is a great opportunity for information sharing and things like that. And I am so deeply sorry that I am not able to join you today on site. So I'm going to start with something that we all know, the need for spectrum, and the need for spectrum is growing exponentially. I will start by giving a sense of how much spectrum will be needed to achieve the full potential of 5G and NextG. I will argue that spectrum sharing is going to be the only practical way of realizing this target, because there is no enough spectrum. There's not enough spectrum to meet all the demands, and the spectrum is a fixed resource. I will talk about some of the current ways of doing spectrum sharing, and I will also point out the shortcomings that we have in these current methods. I will then argue that the best way to mitigate those shortcomings are by using AI/ML techniques through the way of RIC, which is a RAN intelligent controller. And I will also argue that Open RAN architecture and framework is really needed to achieve the configurability, reconfigurability that is needed to achieve the spectrum utilization that we're talking about. Finally, I'm going to talk about two real-world use cases that will illustrate how we can use RIC and open architectures to achieve the outcomes that we are after. The first example would take advantage of some of the existing interfaces and architecture that is already available in organizations such as O-RAN Alliance. And the second one would point out some of the additional interfaces that would be required to achieve full performance benefits. So that is also something that I would like everybody to take a note of, because this is something that is very important. And my goal would be to motivate all of you to think about this problem and see how we can add these additional interfaces to the specification that would be needed to achieve this. So that will be the goal for today. So I'm going to start with the need for spectrum. And we all know that the spectrum is the lifeblood of mobile industry. The diverse set of applications that NextG is going to support or will need to support will depend on spectrum in all the different regions of spectrum, the lower band, the mid band, and the high band. But the mid band is going to be the most desirable band. Why? Because it has the right set of coverage and capacity. And GSMA estimates that to achieve the full potential of 5G, as laid out in IMT 2020, we will need about 2 gigahertz of mid-band spectrum and about 5 gigahertz of spectrum in the upper band. So this is millimeter wave bands and anything about 24 gigahertz. And if this is the requirement for 5G, obviously the requirement for meeting the specifications of 6G will be much higher. So we expect that to meet IMT 2030 requirements, which is the document for 6G, requirements document for 6G, would have a lot more stringent requirements in terms of spectrum availability and spectrum needs, way more than what is estimated for 5G. And it is also very clear that the companies and operators value spectrum a lot, right? So because if you see the recent C-band auction that happened a couple of years back, it went that the auction itself fetched $84 billion, which is a testament for the fact that the companies really value this resource. So spectrum is going to be as significant. It's going to be vital for the success of 5G, 6G, and whatever is going to come after that. And the main question here is that we don't have a lot of spectrum that is available, and we cannot create more spectrum at will. So now the question is, we need all this spectrum in the lower and mid bands, but several incumbents are already occupying those bands. And these incumbents are mainly federal incumbents, DoD and other federal users, that cannot be relocated, or in some cases should not be relocated because of national security reasons. So even when they are able to relocate, the cost incurred by relocating them will be significant. So you might also think that the problem is only with lower and mid bands, but that's not true, because in higher bands, we have passive scientific users. So even though the bands, the spectrum that is available in higher bands is significantly higher than what you have in lower and mid bands, we have incumbents that are scientific users. And we need to protect them. So the lower bands, it's all active users. In the higher bands, it's mainly passive users that have very high sensitivity. So the requirements to coexist with these different incumbents are also very different. So one possible way to mitigate this is by densification, right? So densification is just adding more and more base stations and so on. And even though we might think that is going to be a good solution, there are a lot of issues associated with it, right? Because we cannot relentlessly increase the density, because that is going to cause all sorts of problems with interference and so on. And even when you are able to do this, it's also cost prohibitive, and it will also generate a lot of carbon footprint and so on, which is against the target and requirements for next year. Because energy efficiency, sustainability is an important factor that we need to consider while designing next generation communication systems. So what we are going to argue here is that the only feasible way to do to meet the spectrum demands is by sharing. And the reason why I am very hopeful here is that when you look at these 5G and 6G, they come with a lot of sophisticated knobs that you can use to achieve coexistence. So when I say coexistence, I'm talking about two systems using the same resource in such a way that one system is not interfering or not bothering the other system. So it's basically two systems operating in such a way that they get the whole spectrum for itself. And that's possible because of all these sophisticated knobs and techniques that we have with the newer technologies. So that was not possible with 4G, that was not possible with previous generation, but we have a hope here because the newer generation are coming with all these different sophistication and techniques and knobs that we can utilize to achieve the outcome that we are interested in. So as I said, this is a problem that is that has been around for some time, and we have been doing this since probably even 4G. And there are two techniques that I would like to point out, even though there are some slight modifications to these techniques that are okay. The first one is what we call as the exclusion zone. So exclusion zone is a very simple technique where the geographical area in the vicinity of the incumbent is going to be protected. And it is the area where the licensees are not allowed to have active radio transmission. So it's basically a geographical separation that you do. Very static, very simple to use, but it's also very inefficient. And the problem is that this is a scarce resource. Spectrum is a very scarce resource, and we cannot let any sort of inefficiencies in the operation. The other important aspect is that by doing exclusion zones and protection zones will inadvertently exclude a lot of non-interfering users. So even if you are not really causing any issue, you will be removed from transmission. The second approach, which is also more sophisticated as well as something that has had success, is the database-based approach. So database-based approach is basically information sharing about access rights and usage through some sort of a database sharing mechanism. And the prime example for that approach is the CBRS. CBRS, most people would consider that as a very, very good example, very successful system, but there are also some known shortcomings associated with it, right? So long evacuation times and slow inter-system coordination time, these are all things that are associated with CBRS. And the reason for those things are quite known. It doesn't take into advantage the technological aspect. It's a technology agnostic system. And also the models that are used are very primitive. And those were developed in 1950s and 60s, doesn't take into consideration all the new information that we have. So the CBRS as well as this database-based approach is good, but it's not really good enough to take advantage of all the advanced capabilities that we have. And it is not really operating at a level that we need in terms of efficiency. What we need is really a fine-grained control of all the aspects, right? So we need to be able to control not only at the cell level, not only at the node level, but also at the lower level, such as the user level. And maybe even at the sessions that are happening within the user, right? So you should be able to fine-grain, you should be able to control them in a very specific and very granular manner so that you are not having policies that would affect the entire system. One example here is what is shown in the picture on the right-hand side. We don't want large areas to be affected by the presence of an incumbent. So in this case, the incumbent is a Navy radar. When the Navy radar shows up, you can see that the large area is being protected. We probably don't want to do this because it's going to really reduce the efficiency. So what do we do? So there are a couple of things that we need to do. One is we need to figure out what is the optimum way of doing sharing. So that's the what question. Okay, what do we do? The second thing is that we also, once we know what to do, how do we actually implement those policies and techniques in the system? So for the what question, I would like to point out that next generation systems will be very complicated, will be very dynamic in terms of the environment. It will have likely thousands of base stations and millions of users if you consider even a small region. And that complexity will make it much more difficult to model and predict and control. So what we want to do is we want to rely more on experiential and model-free approaches rather than the models that we have right now. So we want to rely more on the AI-driven, AI-based approaches that will possibly present us with the right sets of policies for spectrum, for sharing, and so on. Once we have that policies, we want to be able to, as I said before, we want to be able to control the system in a fine-grained way. And that's why we need programmable networks, right? So programmable networks where there are open interfaces and there are disaggregated components. So this is what you all know that Open RAN framework provides us. So what should be provided by experiential networking as well as data-driven networking, which is a component of the RIC, and the how part will be provided by the open interfaces and so on. So all the programmable networks, disaggregated networks, and so on. So that should be the main way by which we can get to this.
Thank you. You have about 5 minutes.
Okay, sure, yeah. So now I'm going to get to the two use cases that I mentioned. one is a use case where there is a sharing between government satellite system and a cellular system that is sharing the L-band with the uplink of the cellular. So the government satellite system is using L-band to transmit the meteorological data to a ground station, and the cellular system is using that same band to transmit the uplink from the user to the base station. So obviously, the transmissions of the uplink can cause interference to the downlink of the satellite system. There is also, you can see that there is an RF sensor that is used in the vicinity of the ground sensor that can transmit information to the base station regarding any interference violations that it sees. The simplest way of doing this is to, as I said, is to have protection zones. So area around the government satellite systems would be considered as a protection zones, and nobody will be allowed to transmit there. Obviously, that's a very costly solution in terms of low utilization. So the better way to do this would be to take advantage of what we have from the RAN intelligent controller, right? Number one, what we know is that the satellites don't appear all the time. Typically, it's visible about 15 to 20 minutes or 12 to 15 minutes, and it's going to show up only like 15 times a day. So you're talking about probably around 3 hours out of 24 hours that the satellite is visible. And that's a time when you want to even activate the spectrum management system. Number two is that once you know that it is active, you also get interference reports from the sensor that I was talking about. And the cool thing is that we are able to figure out exactly which operator, which cell, and in some cases, which user is causing the interference. So once you have that information, you have the fine-grained control that we can achieve using RIC, right? Because the RIC is able to manipulate every single user. In some cases, you can even manipulate the sessions within a user, right? So what can you do if you know that the user is the one causing, a given user is the one that is causing interference? You can hand over that user to a different frequency if that frequency is available. You can reduce your power, right? Because if you think about the power control equation, there are different components of the UE transmit power that would be dependent on the traffic, on the path loss, and so on. Obviously, you cannot change the path loss because you cannot really change the location of the user. But what you can change is the data that is allocated to the user. If the user is allocated less data, the user is going to transmit less power, which means that the interference will be less. So you can go and manipulate multiple different dimensions of parameters and configurations with respect to a single user, and that is going to provide a significant improvement in the performance, right? Because you are now letting all the users and all the systems operated as if there is no other incumbent. You are only making slight modifications to the performance of maybe one user, maybe a couple of users, that's it. So it's a significant more, it's a significantly better way of doing things than the protection zone. The second one is going to be a little bit more complicated, which is the sharing between the airborne radar and a 5G system. So you can see that there is an airborne radar that is flying over a geographic region, and you have all these base stations that are transmitted. The important aspect here is that because the base stations are at an elevation with respect to the users, the transmitting beams are all pointed downwards. So there's no issue from the main lobe of those transmissions. However, you could see that in some cases, the side lobe, as indicated by this orange, is pointing towards the incumbent. So what we need to do is that, one, we need to be able to sense the presence of the incumbent. It could be using some sort of a technique that would take advantage of the existing infrastructure, or it could be a capability where the incumbent itself is informing the entrant. So regardless of what we use, once we know that incumbent is present, we should be able to manipulate those beams in such a way that the users are getting the throughput that it is expecting. At the same time, there is no interference to the radar. How do we do that? If you can see on the right-hand side, the SMO can get information about the presence of the aerial radar. And once we have the presence of the aerial radar, the RIC can now synthesize an ideal beam that is in such a way that it is providing all the information, all the requirements for the users, at the same time not causing any interference. So on the right-hand side, you can see that the ideal beam that the RIC has synthesized has no side lobe towards the aircraft. So you can see that ideal beam is characterized by all this beam width table, beam weight tables, and beam characteristic table that can be directly injected to the radio unit, so that it can manipulate all the beamformers and so on. Now, this is what is required to achieve the full potential of this approach. However, right now we don't have this interface that is available. So there is no interface that is available that goes directly from RIC to the RU. And that is one of the things I think that we should focus on. Having such an interface would be something that would be very valuable. So I know that typically Ashutosh asks this question of what should we do next, right? What are things that we could focus on? And this, in my opinion, is one of the important things, adding these additional interfaces. So we have interfaces like A1, E2, F1, and front haul and stuff like that. But having an interface that is directly helping the RIC to manipulate the RU would be very, very useful.
Thank you. I'd like to wrap it up.
Yeah. So I'm on the last slide. Spectrum sharing is going to be the norm of the future. And what I want from this talk is really to motivate you with the importance of this problem, right? So we want standardization bodies to be taking notice of spectrum sharing as one of the use cases. And we have a meeting tomorrow, and I would like to say that, this is something that I think we should all see the value, and we should all try to standardize some of the things that are absent in today's specifications. So with that, thank you so much. And I'm ready to take any questions that you may.
Thank you, Venki. You may just want to stop sharing. I'll just like to say a few things here. Let me see if I can. Yeah. So I guess very interesting. There are a few questions on the chat if you'd like to answer those. But let's thank the speaker first. Venki, you have been a frequent speaker. Hope you can join us next time as well.